Sorry, this is a bit off topic, but yeah, superficially from particle physics, but I hope I can convince you that by the end of this talk that even though it seems like a particle physics talks, the techniques we use here and more importantly, the questions that we ask have much in common with statistical physics and thermodynamics. Yeah, I want to talk about the phase transition, which is common, I would imagine a common theme of interest here, but with specifically the phase transition of strongly interacting matter or nuclear matter, for which we actually have a theory. I guess the one difference between STATPHYS and particle physics is that here we have a theory, so we are we are not free to construct models, though we do try that from time to time, but rather we have to work from the ab initio theory every now and then. It's a nonlinear theory, like many of the statistical physics models that you consider, and because it's nonlinear, very often what we have to do is we have to give up trying to get an analytic expression, and we have to simulate it numerically. What we do is we do Monte Carlo, and the question here, okay, to set the stage maybe before I talk about the Monte Carlo process, the question here is about a phase transition called the chiral phase transition. Thing is, massless Dirac particles, quarks, which are the matter particles of QCD, are actually Dirac fermions. And in the massless limit, they can be either left-handed or right-handed. This symmetry is called chirality, which actually borrows its name from chemistry. On the other hand, suppose I have n massless flavors or nf massless flavors, then the way the QCD action is set up, it's actually symmetric if I just interchange these flavors. So what you have is actually you have this enlarged symmetry group where each particle has a chiral symmetry, and then you have this additional NF symmetry, and this combined symmetry is what is called chiral symmetry in QCD. And the next thing is that for more than one flavor QCD is paramagnetic, but n flavor QCD you actually have spontaneous breaking of this chiral symmetry in the vacuum state. This breaking actually explains the low energy spectrum that we see, the low energy nuclear spectrum. But this broken symmetry we now know is actually restored at very high temperatures. These are temperatures of the order of 10 to the 12 Kelvin, which sounds pretty large, but it's actually smaller than the electroweak phase transition, which has consequences for the early universe. This is actually a lower temperature. And a second reason why this phase transition doesn't really have consequences for the early universes, unlike the electroweak phase transition, it's just a crossover. It's a smooth analytic transition. And what we now know is actually that it's the nature of the transition actually depends on the number of flavors and on the masses of the quarks. So for 2+1 flavors and physical quark masses, this is actually a crossover transition. This was something that was found out only recently, about 10 or 12 years ago. And you had to do Monte Carlo simulations. And here what I have is not the original work, but one of the recent things that shows that the susceptibility, that is to say the fluctuations of the order parameter, they actually saturate with increasing volume. They do not show a marked volume dependence, either anomalous or canonical, which means that it's not a first order transition, not a second order transition, it's just an analytic crossover. And very quickly, I don't need to introduce Monte Carlo to this audience, but the only thing I guess I could say is that the first thing you want to do when you're simulating it is you want to discretize it. So far, so straightforward. We put the matter fields, the quarks, on the sides of a 4-dimensional lattice. The only difference is that the force-carrying particles, the gluons, are what we put on the links connecting two sides. And this construction actually preserves a symmetry which is very dear to us, called gauge invariance. It's a symmetry of the continuum, and when constructed this way, Ken Wilson was the one who showed this construction, how this works. It actually preserves gauge invariance even in the even when you are breaking other symmetries like Lorentz or translation symmetry, for instance. So you discretize it, and Dirac particles are four component particles. You have a four-dimensional lattice. Gluons tend to be 3 by 3 complex matrices, so that's 18 real degrees of freedom per site. So the number proliferates pretty quickly. You have a path integral, but because of the discretization, it's now a multidimensional ordinary integral, but it's a very high dimensional integral. So what you have to do is you have to do Monte Carlo simulations. You generate a set of configurations called gauge configurations, and then you measure the observable of interest on each of these configurations, and finally you do an ensemble average. And this is in some sense the, this is what is called a Columbia plot. This is sort of like the fundamental figure for this kind of questions. It was based on work done by these two gentlemen back in '84. They basically showed that you have a second order phase transition, or they conjectured, they didn't work from QCD, they worked from a model. They conjectured that for 2 flavors in the massless limit, you have a second order O4 transition, but for 3 and higher flavors, the second order becomes a first order transition. Basically, the beta function does not have a non-trivial fixed point for greater than 2 flavors. And on the other side, when your quarks are so heavy that they're almost decoupled and all you have in the theory are gluons, then again you have a first order theory. So this is sort of what we believe is the underlying picture, but it's something that needs to be verified from first principles. So that's basically what has taken us probably the last 30 years, and we are still sort of, as you will see, quite far from knowing the final answer to this. So here's the thing. So this is the phase diagram. This is the light quark axis, the strange quark axis. The right and upper corners are where these quarks are so heavy that they're decoupled, essentially. Let's say our physical point is somewhere here where we have a crossover transition. Now, if I keep the strange quark mass fixed and I move and I decrease the masses of the light quarks, depending on where this physical point is, I could actually hit either an O4 transition or the boundary of the first order transition, which is just an ordinary Z2 Ising model second order transition. Or if I'm really lucky, I could actually encounter the tricritical point, which is just the intersection of 2 different second order curves. And based on that, actually, though I will not talk about it here, if I introduce a chemical potential, it tends to have consequences for the nature of the phase diagram in this E mu plane, for instance. For example, if it's just a second order if it's just a crossover, I'm sorry, this should say, yeah, if it's just a second order transition and I turn on a chemical potential, it'll stay that way. It'll encounter a critical point at one point and then become a first order. But if I'm at the tricritical point, then I actually have the critical point right on the y-axis, and then I have a first order transition the whole region, in the entire region. And this is actually, determining this picture and especially the location of the critical point is actually something that is an ongoing experimental, it's the focus of an ongoing experimental program, but I won't touch upon it anymore. So the point is, how do I determine what is the, so taking the chiral limit is straightforward. I have a Baire parameter, which is my quark mass, and I just tune it. And although it's a Baire parameter, because you do have a chiral symmetry, Baire m going to 0 does imply a renormalized m going to 0. So I just tune it towards 0. That's actually difficult because the time to generate a single configuration actually scales as some power of the, some inverse power of the quark mass. So it's not easy to go all the way down to the chiral limit. Actually, at m strictly equal to 0, the time for a single configuration is infinity. But what you can do is you can generate various quark masses, and then you can look for signs of scaling. And this is okay. We believe that, it should be O4, but 3-dimensional O4 because it's a finite temperature transition. And the other thing is, one lattice artifact is this O4 actually breaks down to an O2 remnant. But that's okay. If we can see an O2 scaling, that's still a first, I would say, a first piece of evidence that it's actually O4 in the continuum. One problem, actually, nothing is ever that simple. So the good news is that these simulations were done with various quark masses, and then you have this kind of scaling curve, which would actually a priori make you very happy. You see that you do have O2 scaling. You have to subtract a piece which comes from the regular path. That's okay. But once you do that, you actually see O2 scaling. The only trouble is O2 and Z2 critical exponents are actually quite similar. So it seems that you can actually fit the same data to Z2 scaling as well. I don't have exact numbers, but O2, O4, and Z2 are actually within 10% of each other, these critical exponents. So that's somewhat of a setback. One consolation prize that you get from this whole thing is that the H field, for example, the symmetry breaking field parameter in the case of Z2 involves this M critical, I'm sorry, not M critical, it involves this X intercept where the quark mass line will meet the Z2 line, and you can still put a kind of upper bound on this X intercept, and it seems to be roughly 10 MeV. Just to give you a rough estimate, a physical world pion is about 140 MeV. So 10 MeV is still rather small. It means that even if it's Z2, the physical point is still somewhere very close to this upper line. So that's as far as the 2+1 flavor theory is concerned. A harder calculation is to actually look at the 3-flavor chiral limit. This involves making all 3 quarks massless, and as you can imagine, that's even more challenging. Here actually there's been, it's actually been I just need a minute more. It's been the topic of quite some interest, because when the first studies were done, immediately people found a second order Z2 transition with a pion mass which was almost double our real world pion mass. Unfortunately, when the study was repeated with a finer lattice spacing, and you always have to take the spacing going to 0, this pion mass shrank very rapidly. So more recently, there have been several other calculations, and all of these tend to yield rather discouraging results, as you will see. This is our latest study where we went all the way down to 80 MeV in the pion mass, and we looked at the Bind accumulant, and you see that the Bind accumulant actually just, it's consistent with its value for a crossover. So it doesn't seem to indicate any sign of, or any hint at any sign of a second or first order transition, even all the way down to 80. And at the same time, there was a Japanese group that also did a similar calculation with a different discretization. They also had an initial good news. They got the same thing. They got about a 300 MeV pion mass, but the same story when they repeated their calculation, as you can see with finer lattices, the 300 has come down all the way to up to about 100 MeV and counting, I would say. So, yeah, to sum up, I mean, it's an open question. The phase diagram of nuclear physics of strongly interacting matter, it's an open question. That's a bit sad, because initially there did seem to be, it seemed that we were close to an answer, but unfortunately nature is apparently not that kind. But we still do know a bit. We know that the pure gauge transition, this was something which we found from Monte Carlo, that it's first order. It was not a prediction of the original theory. And similarly, we also know something, we can say something definite about the world we live in. It's the transition at physical quark masses. However, even though it's a question of interest, unfortunately at this stage I have to say that the nature of the transition is still unresolved, but it's nevertheless important because there is an ongoing experimental search for this QCD critical point. So depending on how this pans out, we might or might not see something in these experiments. So anyway, but it's hoped that we have no option, we have no alternative but to keep working, keep pushing at it, and hopefully in the future we might have a more definite answer. Thank you. Yeah, that's right actually. I mean, more to the point, tricritical is where a second and first order, but then maybe it's my mistake. I mean, I just meant the point that you have two different second order lines here. This is an O4 line and a Z2 line. and you have them meeting at one point. Yes, this is a second order from but O4 universality, and this being the boundary of a first order, it's just Z2. This one, right, right, right. And there's no particular name for a meeting of two second order lines. So there is the chiral condensate, psi bar psi. It is not invariant under chiral rotations. So a non-vanishing expectation value for psi bar psi implies a spontaneous breakdown of chiral symmetry.